So our next speaker is Luis Garay. Luis is a professor at Universidad Complutense de Madrid. His extensive research ranges from QFT and Q spacetimes to emergent gravity and analog models in Bose-Einstein condensates. And today he's going to talk about black semiclassical stars. Luis, whenever you want, the floor is yours.
Okay, so good night. Thank you very much, Jose and Eduardo, for inviting me to this wonderful workshop. Well, it is Friday night here in Madrid, so wine and tapas are waiting. So let's get into business, and I hope you enjoy the talk. So what I'm going to talk about can be summarized as what the title says: black semiclassical stars. The idea is, can we find some ultra compact object that replaces the model of black holes for those for those astrophysical dark and compact objects that we are calling astrophysical black holes. So this work is based on what we've been doing for the past few years in collaboration with Carlos Barteló and Raúl Carvalho Rubio and Julio Rechea and Valentin Boyanov. I must say that Julio and Valentin are the real experts in the topic, so I'm reporting on basically their work. We all know that general relativistic black holes predict the existence, that general relativity predicts the existence of black holes. That is to say, objects that have two main characteristics. First, that not even light can escape from them. That is to say, they have horizons, and also they have regions, points, whatever, of infinite density. That is to say, singularities, where we cannot use or where laws of physics do not apply. We don't know how to deal with those singularities. And at least from my point of view, these are very strange features indeed. Okay, so this sort of a horizon, things can get in, nothing can get out, and singularities with infinite densities. However, we know not by now very well that there exist objects that I'm calling astrophysical black holes. These are bodies in the universe which are very dark and compact, and the question is, these very dark and compact objects are really black holes in the sense that I've been just talking about and that we all know, or are they very, very ultra compact stars with horizons with surfaces very close to their gravitational radius? So for the time being, observations cannot tell, and I must also say that general relativity, of course, explains these objects very well with something that I really like, which is mathematical elegance and simplicity. However, quantum physics may well change this paradigm through two aspects. First, black hole evaporation, and second, singularity regularization. What I mean by that is that first, we have these singularities with infinite densities, and probably quantum theory will have something to say about them, and probably our quantum theory of gravity will be able to regularize those singularities. Perhaps without affecting the horizon, that is just removing the infinite part in the core and not changing the horizon structure. But in that case, we know what is happening. We have black hole evaporation, which is in my opinion, absurdly long time, proper time, characteristic time, which is 10 to the 60 something, so 67 years or something for a typical black hole of the size of the sun. And this is what gives rise to loss of information. There exist various models for long-lived regular evaporating black holes, like the sort of things that I'm telling you, with horizons that are slowly evaporating. I'm not getting into any further models. I just want to say that they've been in the market at least since the 80s. The first models that I know of are by Frolov and Vilkovitsky. But the question again that I would like to address in this talk is, and that we've been working on for the past few years, as I was saying, is whether this is the final stage of gravitational collapse, or whether there are other possibilities. And of course, the point of view that I'm going to try to take in this talk is the latter one. There are other possibilities. So in order to explore these possibilities, let me briefly get into semi-classical gravity and the kind of summary of what I'm going to be talking about in this talk. So general semi-classical gravity in semi-classical gravity, what we do is use Einstein equations, but not only with the classical stress energy tensor, but also we have a quantum source, which is what we call renormalized stress energy tensor, and it comes from quantum effects from fields living on a background. So we are dealing with back reaction, okay, here. So first, we need to know what this renormalized stress energy tensor is, and we are going to be dealing only with massless scalar fields just for simplicity. Once we have these equations, we are going to look for static solutions. First in vacuum, that is to say, without the classical energy momentum tensor and just sourced by our quantum renormalized stress energy tensor. And then we are going to try to find static configurations with matter, at least with very simple classical matter there. And the question that I want to ask, as I told you before, is can ultra-compact semi-classical stars exist? That is to say, static situations for stars that have their surface very close to the gravitational radius. Then, once we analyze the static part, we are going to deal with dynamical configurations, and this means that mostly we are going to be concerned about horizon formation and whether that is a stable process. And all this, as I think I've told you already, is with the idea of trying to go towards models that give you new equilibrium semi-classical ultracompact objects that can describe what we know as astrophysical black holes. So let me start first describing then very briefly the renormalized stress energy tensor. For that, we are going to use as vacuum state in which we calculate the stress energy tensor, the Bolwer vacuum. Why is that? Because we are going to be concerned with static and asymptotically flat stellar-like solutions without horizons, so the natural vacuum would be Bolwer vacuum. Or if we are dealing with collapsing situations, with collapsing stars, we will be using the in vacuum. That is to say, we will start with a vacuum that in the past behaves very much like Minkowski's vacuum, and in the future will behave in whichever way it has to, so that it keeps its Hadamard nature. This renormalized stress energy tensor can, and in general does, violate energy conditions, and therefore it can be a source of repulsion, of gravitational repulsion. And this repulsion may allow for new equilibrium because this repulsion may compensate the gravitational field. The main difficulty with the renormalized stress energy tensor is that if you try to calculate in 1+3 dimensions in our 4-dimensional world, it is extremely complicated and very difficult to calculate. So what we have to do is to resort to approximations. So the first approximation that I'm going to talk about is, again, very well known, is Polyakov's approximation. In this approximation, what we do is we just take the TR, the time radius sector of our spherically symmetric, for instance, space-time, and take just this sector, ignore every potential, everything, backscattering, and so on, and then we end up with a 1+1 conformally invariant space-time. We calculate the energy momentum tensor there, and then we go to 1+3, adding the, or much better, dividing by the surface of a sphere as usual. This approximation is very good for black holes. That is to say, whenever we are away from the origin, from the singularity in which obviously this factor blows up. But again, if you try to use this stress energy tensor to find quantum fluctuations, quantum corrections, back reaction on standard stars like the sun, this is not going to work, again, because at the origin this blows. This tensor can be made divergence-less for static configurations. However, it doesn't work for dynamical ones. As I said, it ignores back scattering. And another good feature is that it depends only on the metric, on the derivative of the metric and its second derivative. So it doesn't change the order of the semi-classical Einstein equations. And I mentioned in this because in general, renormalized stress energy tensors have higher derivatives. To solve the problem at the origin with this stress energy tensor, what we are going to do is to consider regularized Polyakov approximations. That is to say, we are going to replace the 1/4 pi r squared by some function f of r that behaves very much like Polyakov's, except in a small region around the origin. So in the end, what we're doing is just regularizing by hand the Polyakov stress energy tensor. In that case, what you can obviously see, because we are constructing it with this aim, this stress energy tensor is negligible for regular large stars like the sun or equivalent. Although I'm not going to give you the details, we are also going to use a better motivated approximation, which is what we call the order-reduced approximation to the Anderson, Hiscock, and Samuel renormalized stress energy tensor. This approximation has nice features. Again, now it depends only on the second derivative of the metrics. Well, first, of course, on the metric itself. It is four-dimensional, properly speaking, and it is regular at the origin. And for instance, if you take Schwarzschild's spacetime, it coincides with the Anderson, Hiscock, and Samuel stress energy tensor, which is just the stress energy tensor. There are other options that we haven't worked with because, as I said, they are very difficult to work with. They have high derivatives. You have to use numerics and so on. So the work that I'm reporting here is done with these two approximations. First, with a regularized Polyakov, and in general, with a better motivated order-reduced approximation to the Anderson, Hiscock, and Samuel stress energy tensor. The way in which we do the reduction is just we plug it into the semi-classical Einstein equations, we expand to h squared, and then we write to that level of approximation, to that order of approximation, higher derivatives in terms of the lower derivatives, and then replace them in the stress energy tensor. That is the idea that is behind this order reduced. So once we have the stress energy tensor, now the renormalized one plus the classical one, now we go to solve the Einstein equations, the semi-classical Einstein equations. And first we look for vacuum configurations, that is to say, Einstein equations in which, semi-classical of course, in which the classical tensor vanishes, so we have empty spaces, so to say, and we only have the renormalized stress energy tensor as a source. And what we have done is to find a complete set of self-consistent semi-classical vacuum solutions. So we have the whole catalog solving these semi-classical Einstein equations in static and spherical symmetric space-time. And the interesting result is that none of them is regular. The only one, well, of course, except Minkowski, that is the only one that is regular. Also, all these solutions none of these solutions show a horizon. Rather, the horizon is replaced by a throat that is connecting our asymptotic region, asymptotically flat region, with an inner singularity, which generically, it is a time-like singularity. So the lessons that we obtained from the vacuum analysis is that we have strong evidence that vacuum semiclassical gravity does not allow for regular asymptotically flat geometries. And also, we have to take into account that does not allow for this, provided that we are dealing with static spacetimes. That is to say, we cannot have regular asymptotically flat geometries with static horizons. So matter content is necessary in order to obtain regular consistent geometries from the semiclassical point of view. So let's go to the semiclassical part. So what we have done again is try to solve the semiclassical Einstein equations in spherical symmetry, but now with a classical stress energy tensor plus the renormalized one. And for that classical matter sourcing the Einstein equations, we are going to use just constant density fluids for simplicity. And in that case, again, what we have done is to find a complete set of self-consistent semiclassical solutions with constant density. And we have found configurations that are what we are calling sub-Bugdal, super-Bugdal, regular, quasi-regular, non-regular, and so on, all sort of situations. So before I go to discussing the main results, let me remind you that Bugdal's theorem in general relativity is telling us that in spherical symmetry plus some other hypotheses that are not really relevant here, the compactness, that is to say twice the mass over the radius of the star, cannot be larger than 8/9. So when we are dealing with sub-Bugdal, what we mean is that we mean configurations that satisfy this theorem are within these bounds of 8/9. And when we are talking about super-Bugdal, this means that we have very compact stars that go beyond this compactness. And with regular, quasi-regular, non-regular means stars that are either regular at the origin, of course, or almost regular, that is to say they are regular except in a very small region close to r = 0, and maybe well due to the approximations that we're using, or even non-regular at all, as that was the case in vacuum, as I was discussing. Again, what we have found among all this catalog is, first, just to mention the regular ones, what we have found is, of course, if we remove the renormalized stress energy tensor, what we have found is classical sub-Bugdal stars, that is to say, our standard stars. Those are solutions, of course, because I'm just removing the renormalized stress energy tensor. This is what we knew from the past. This is just a consistency check. But also what we have seen is that if we are in not so compact stars, so they are sub-Bugdal in the sense that they satisfy Bugdal's theorem, and we introduce the quantum fluctuations, we can still find these quantum or semi-classically corrected stars. So no surprise there either. Where the surprise comes, and this is what really is the result that I'm most interested, is that we can find semi-classical configuration solutions to these semi-classical Einstein equations whose compactness is very, very close to 1. That is to say, these are stars that have a surface, its surface very close to their would-be horizon, to the gravitational radius. And here are just a couple of graphics just to give you an idea. So the point is, if you have a look at the figure below, we have a region, an outside region, the exterior, which is just vacuum, slightly corrected by semi-classical fluctuations. The whole star except the center, which roughly obeys Polyakov's approximation, and it's just what you would have for a geometry corrected by the semi-classical stress energy tensor. And we see that we can have a regular region close to the origin. In practice, if you have a look at the G00 component, that is to say the exponential of this phi, you see that it reaches a finite value, and the compactness as you go to r = 0, it reaches 0 as it should be, because the matter contained within smaller and smaller sphere is smaller and smaller. So this is what we mean by having ultra compact stars that in that sense behave very much like the large regular ones in that sense. So the story so far is that there do not exist regular semiclassical static self-consistent vacuum solutions, but there exist regular semiclassical self-consistent dense ultra-compact stars. So we need matter if we want to make semiclassical and consistent stars.
Luis, you have 5 minutes left.
Okay, so the summary from this is that if I have a star that is collapsing, there are two options. Once it stabilizes, it can follow Hawking evaporation paradigm with non-static horizons because they are sort of shrinking little by little and potentially lose information. Or the other possibility, which is the one that we are advocating here, is that they find a way to settle to an ultra-compact static equilibrium configuration without horizons. And whether they have Hawking radiation or not is just an entirely different matter. If we talk about dynamical collapse, I'm going to skip most of it because I don't have enough time. But the point is that when we are dealing with dynamical collapse, we can have a huge build up of renormalized stress energy tensor close to the horizon and or the would-be horizon, and this may change completely the evolution of the star. So first, what we have done is analyze the back reaction on the external horizons, and in external horizons, what we have done is analyze different ways in which a star is collapsing towards the horizon, and we have seen that we can have Hawking-like radiation even without horizons. That was seen by Carlos Barceló and collaborators in 2006. And depending on the speed of the collapse close to the would-be horizon and why this speed could change, of course, within general relativity, we have no choice, but there might be mechanisms for slowing down the collapse. Then we will have a buildup of renormalized stress energy tensor, and the back reaction could be important. So in these two situations, when we are crossing the gravitational radius at low velocities, or either when we are approaching the formation of the horizon, the renormalized stress energy tensor may become large and then change because the whole thing because of back reaction. So classically, black holes. Now I've been talking about the external, okay, the event horizon, but typically we have inner horizons as well. And the situation that we have classically, let's say from the general relativistic point of view, is that outer horizons move outwards just because the star is accreting matter, the black hole is accreting matter. And the inner horizon moves inwards when it is accreting matter. But on top of that, what we have is the mass inflation instability that was discovered by Poisson and Israel, that makes the inner horizon to shrink even further. So this is what is happening classically, but if we introduce the renormalized stress energy tensor as a source of perturbation, then the whole thing may change. Outer horizons slowly evaporate inwards again because it is emitting Hawking radiation because of the back reaction, but inner horizons, instead of shrinking further, the back reaction action makes just to do the opposite as Hawking, as outer horizons, and therefore they tend to evaporate outwards. And actually that's not a kind of evaporation in the sense that it's a slow process. It's very much something like an explosion. So what we see is that from the semiclassical point of view, the evaporation is an interplay of inner horizons, is an interplay between mass inflation that makes the inner horizon to shrink and the vacuum polarization that makes the inner horizon to explode, at least initially. So what happens depends very much on the specific dynamics that we have. So in the last minute, I just want to mention that because of this, we can face different future evolutions for this collapsing matter. First is the one that we know, Hawking evaporation, that in the end ends up in a naked singularity or a remnant or whatever we know from the 80s, 90s, and so on. But there is another option, which is the evaporation of regular black holes, which is what I told you before. That is to say, the inner horizon stays or shrinks because of the mass inflation instability, and the outer horizon shrinks a little bit as well, and very, very slowly we have long-lived Hawking-like evaporation. But this is unlikely because, as we said, of the instability, the semiclassical instability of the inner horizon. And if this instability really takes place, what we expect is that the inner horizon grows, the outer horizon shrinks, and we will have a very short-lived process with a regular matter field, ultra-compact core that probably evolves to a new form of stellar equilibrium that depends very much on the dynamic, and this has to work out. I'm out of time already, so my last comment is that there is another option which goes beyond semiclassical gravity, and we've been also proposing and discussing in the past years, which is that it collapses at some point, it reaches the quantum region in which the stress energy tensor is huge, and then we have a repulsion, the star comes out again, but because of dissipation doesn't reach the initial point, so collapses again and bounces once and so on, and because of dissipation, this initial situation in which the next stage collapses is closer and closer to the gravitational radius, so it would cross this gravitational radius slower and slower, and then again the vacuum polarization can build up and reach and make it reach a new form of stellar equilibrium. So I think this is all I have to say, because that's it. So thanks very much for your attention, and questions, please.
Thank you, Luis, for your very interesting talk. So we have time maybe for, well, let's see, we have two hands. Maybe we have time for these two questions. Ben, go ahead.
Yeah, hi. So one thing that just kind of, there's an interesting kind of dialogue between the work I was discussing and the work you're discussing. I want to ask a question about that. So one of the results that we found is that the presence of a killing horizon is crucial for the decoherence effect that we predict. So, for instance, a star would not decohere a superposition in the exterior, but a black hole would. Are the kind of objects that you're considering, do they have a killing horizon? And could that be a way? Yeah, that's the question.
Yeah. The idea that we have is, I try to convey it, is the following, is that, okay, horizons, yes, you're saying killing horizons, event horizons, any sort of, it doesn't really matter the details here, are very sort of drastic features of an astrophysical object. And so what we are considering is the possibility, and we are trying to justify it by semi-classical gravity and various methods, that actually what we call astrophysical black holes are not really general relativistic black holes with killing horizons, but are just ultra compact stars that probably have a surface that is very close to the horizon. But perhaps one of the main features that we are thinking about is that, unlike black holes that have empty interiors, these are just standards. I wouldn't dare call standard in the sense that they are filled with matter, despite the fact that this matter may be very rarefied, and I don't know anything about the state or what it is. So that is the idea that we have in mind. And so we are trying to find mechanisms that may replace black holes by something like more physical and less mathematical, if we allow me that language, which are filled with matter. In the end, again, philosophically speaking, or whatever you want, the idea that we have, in particular that I have, is that gravity without matter is not much. So having empty configurations sounds weird to me. But this goes much beyond the talk. It's just a sort of the general context that I have a feeling, and I'm not sure whether this answers the question or.
No, yeah, it does. Thank you. Yeah.
But well, I don't know whether we have time. But having a very ultra compact star without horizon, it doesn't mean that it doesn't have something that looks like Hawking radiation, because there might be a tiny evolution there that, of course, if there is, however small it is going to be controlled by surface gravity, and probably there will be some kind of emission similar to that, despite the fact that there are no horizons.
Yes, no, that's true. Yeah, I think, well, we could talk more offline, but I guess
again to what you were asking.
Yeah, I guess the effect we found is independent of the Hawking radiation, and it's hard to see how you would mock it up without a killing horizon, because it relies on the production of soft gravitons propagating from the horizon into the interior. Okay. But it'd be interesting to see if there's any kind of empirical signature of that, but it's a small effect. So, but thank you.
Thank you.
Yeah, so you can continue that discussion maybe in Slack or maybe in the question session afterwards. Albert, please be very brief, because we are tight in time.
Yes. So very nice talk, Luis. So yes, we could have a very long discussion, but actually here I have a very short and simple question just to clarify. The solutions that you consider with inner horizons were because of charge matter that you?
Oh, not necessarily.
Or can you have?
Not necessarily. First, if you take a classical black hole and you remove the singularity for whatever reason, then you create automatically an inner horizon. This is what Hayward and other people saw, but it's very easy to see, because you remove the singularity, you have regular space-time inside, and so you have to convert sort of the ingoing light cones into standard ones. So you need an inner horizon. But not only that, it is also that in general relativity, without changing anything, when a star is collapsing, you have both horizons, except that one disappears and the other one remains.
Right, but you talked even about static configurations, right? So that where you have, right? But there, so you're saying that
the stability of horizons. Actually, we were thinking in this sort of horizons that are created in evolution, or that they are present for whatever reason. But I was not thinking in Reissner-Nordstrom or anything. That could be as well.
Okay, no, that's
clear.
Thanks for the clarification.